Good evening, and welcome to The Gentle Scientist. Tonight, we embark on a journey that is both infinitely vast and intimately close. A journey to explore the most extraordinary place in the known universe. Your home, our home, Earth. This blue sphere, spinning quietly through the darkness of space, holds more wonder than 1,000 lifetimes could uncover. Beneath your feet right now, ancient rocks remember the birth of continents. Above your head, an invisible shield deflects the fury of the sun. Around you, air moves in patterns that connect every breath you take to storms on the other side of the world. Earth is not simply a planet, it is a living symphony, a delicate balance of stone and water, fire and ice, light and darkness. It is the only world we know of where oceans shimmer under moonlight, where mountains rise grain by grain, where life has flourished for billions of years in an endless dance of transformation. Tonight, as you rest, we will drift through the story of this remarkable world. We will touch upon its violent birth among the stars, its perfect position in the cosmic ocean, the thin veil of atmosphere that makes every sunrise possible. We will descend into hidden depths where liquid iron spins to create an invisible shield and rise again to witness the patient work of water carving canyons over millions of years. Each fact is a thread in the vast tapestry of Earth's story, a story that includes you here, now, breathing this ancient air. If you enjoy these quiet explorations of science and wonder, I invite you to subscribe to The Gentle Scientist. Join us as we wander through the mysteries of the universe, one peaceful evening at a time. Your presence here helps others discover these moments of calm curiosity. And if you'd like, leave a comment below telling me where you're listening from and what time it is. Or just share any thoughts that drift through your mind as you listen. But for now, there is nowhere you need to be, nothing you need to do. Simply settle into comfort. Let your shoulders relax. Feel the steady surface beneath you. As your breathing slows and your thoughts begin to soften, know that you are about to discover your home as you have never seen it before. Not as a collection of facts and figures, but as a living, breathing entity. Ancient and ever-changing, fragile and resilient, ordinary and utterly miraculous. Close your eyes if you wish. Let the words wash over you like waves on an endless shore. Just allow yourself to marvel, to wonder, to drift on the gentle current of Earth's extraordinary story. Let us begin at the very beginning, when there was no Earth at all. Only darkness, dust, and the patient work of gravity gathering the pieces of our future home, grain by grain, across the vast emptiness of space. Breathe deeply, relax your mind, and let the story of Earth carry you softly towards sleep. In the beginning, there was no Earth, no blue oceans, no green forests, no mountains reaching toward the sky. There was only darkness, and within that darkness, a cloud, a vast, spinning cloud of gas and dust, drifting through the emptiness between stars. This cloud, called the solar nebula, was impossibly large, larger than our entire solar system is today. And within its swirling depths, the story of our world was about to begin. 4.5 billion years ago, something disturbed this peaceful cloud. Perhaps a nearby star exploded in a supernova, sending shock waves rippling through space. Perhaps the cloud simply grew dense enough that its own gravity could no longer be ignored. Whatever the cause, the cloud began to collapse. Slowly, at first, then faster, the gas and dust fell inward. Drawn by an invisible force as old as the universe itself. As the cloud collapsed, it began to spin. This is the way of the cosmos. Everything that falls also turns. The cloud flattened into a disk, like pizza dough spinning in the air, and at its center, material gathered and compressed. The center grew hotter and denser, the pressure building until finally, wondrously, the sun ignited. A new star was born, flooding the disk with light and heat. But the sun did not claim everything. Around it, in the remaining disk of dust and gas, smaller gatherings had begun. Particles of dust, each smaller than a grain of sand, floated through space and occasionally touched. When they did, they sometimes stuck together. Slowly, patiently, these tiny collisions built larger pieces. Dust became pebbles. Pebbles became boulders. Boulders became mountains floating in the void. This process, called accretion, continued for millions of years. The mountains in space grew into worlds, small at first, but steadily gaining mass. As they grew, their gravity grew stronger, and they began to pull in material from greater distances. The solar system became a chaotic place, filled with thousands of these growing bodies, called planetesimals, orbiting the young sun in a cosmic dance of creation. Among these countless forming worlds, one particular planetesimal was destined to become our home. It grew in the perfect region, not too close to the sun, where heat would vaporize water, and not too far, where cold would freeze everything solid. In this temperate zone, sometimes called the Goldilocks zone, our proto-Earth continued to gather mass, collision by collision, over tens of millions of years. But young Earth was nothing like the world we know. It was a hellscape of molten rock, its surface glowing red and orange with heat. Every impact added more energy, keeping the entire planet in a liquid state. There was no solid ground, no water, no air we could breathe. The atmosphere, if it could be called that, was a toxic mix of hydrogen, helium, and volcanic gases. Lightning crackled through clouds of vaporized rock. It was a world of fire, violence, and transformation. The heat was so intense that materials began to separate by weight. Heavy elements like iron and nickel sank toward the center, while lighter materials floated toward the surface. This process, called differentiation, gave Earth its layered structure, a dense metallic core surrounded by a rocky mantle, and eventually, as the surface cooled, a thin solid crust. Even today, billions of years later, this structure remains, hidden beneath our feet. As Earth continued to grow, it swept up more and more material from its orbital path. The impacts became larger, more violent. Small asteroids struck regularly, adding their mass to our forming planet. Each collision released tremendous energy, keeping the surface molten, like a pot of water that never stops boiling because heat is continuously added. Then, approximately 4.5 billion years ago, something extraordinary happened. Another world, roughly the size of Mars, was wandering through the inner solar system on a collision course with Earth. Scientists have named this vanished planet Theia, after the Greek Titan who was mother of the Moon. Theia had been growing in the same region as Earth, following a similar orbit, until gravitational interactions destined them to meet. The collision, when it came, was catastrophic beyond imagination. Theia struck Earth at an angle, not head-on, but with a glancing blow that was somehow both destructive and creative. The impact released energy equivalent to billions of nuclear weapons detonating simultaneously. The outer layers of both worlds were vaporized instantly, turned into superheated plasma that sprayed into space. In the aftermath, Earth was left spinning faster than before, its surface entirely molten, glowing like a second sun. And surrounding it, held by gravity, was a ring of debris, vaporized rock and metal from both Earth and Theia, orbiting in a glowing band around the wounded planet. This ring stretched across the sky, brilliant and terrible, casting light onto the churning surface below. But the cosmos has a way of building beauty from catastrophe. Within that ring of debris, the same process that formed Earth now began again on a smaller scale. Particles collided and stuck together. Gradually, over perhaps just a few thousand years, a blink of an eye in cosmic time, the debris gathered into a single body. The Moon was born, not from nothing, but from the broken pieces of two worlds. This violent origin explains why the Moon is so unusual. It is enormous compared to Earth, proportionally larger than any other moon in the inner solar system. It is also less dense than Earth, composed mainly of lighter materials from the outer layers of both planets. The heavy iron cores of Earth and Theia remained behind, merging together to form our planet's enlarged core, while the lighter material formed our constant companion in the sky. The Moon's creation had profound consequences for Earth. The impact that formed it knocked Earth into a new tilt, giving our planet its 23.5-degree axial inclination. This tilt, which might seem like a small detail, would eventually create our seasons and help make Earth more hospitable to life. Without it, the climate would be far more extreme, with less temperature variation to drive weather patterns and mix the atmosphere. The impact also sped up Earth's rotation. The young Earth spun much faster than it does today. Days were only about 5 or 6 hours long. The Moon, newborn and close, loomed enormous in the sky, appearing perhaps 15 times larger than it does now. Its gravitational pull on Earth was intense, creating massive tides in the molten surface, pulling it into a slight egg shape that followed the Moon's position overhead. Over hundreds of millions of years, these tides acted as a brake on Earth's rotation. The Moon gradually slowed our planet's spin while simultaneously drifting farther away, stealing rotational energy and converting it into orbital energy. Even today, this process continues. The Moon recedes from Earth by about 3.8 centimeters each year, a pace so gentle we would never notice in a lifetime, but relentless across deep time. And Earth's rotation continues to slow, lengthening our days by about 1.7 milliseconds per century. As the moon took form and the worst violence subsided, Earth began its long journey toward becoming a habitable world. The surface slowly cooled, though it would remain molten for millions of years more. Water, locked in the rocks of asteroids and comets that continued to bombard the young planet, was released by impacts. Steam filled the atmosphere, creating thick clouds that shrouded the entire world. This was also when Earth received many of the elements essential for life. The heaviest elements, gold, platinum, uranium, had mostly sunk to Earth's core during differentiation. But late arriving asteroids, striking after the core had formed, delivered these elements to the surface where they would eventually become accessible. Every gold ring, every platinum catalyst in modern technology arrived as gifts from space during this cosmic bombardment. The same impacts brought organic compounds, carbon-based molecules that would later become the building blocks of life. Asteroids carried water ice, amino acids, and complex carbon molecules formed in the cold depths of space. Earth was being seeded with ingredients for something unprecedented, though it would be hundreds of millions of years before those ingredients could combine in meaningful ways. Eventually, perhaps 4.4 billion years ago, the surface cooled enough for rock to solidify. The first true crust formed, not the familiar granite continents, but a darker, heavier rock called basalt, similar to what covers ocean floors today. This crust was thin and unstable, constantly breaking apart and reforming as heat from below continued to stir the interior. And finally, as the planet cooled further, the steam in the atmosphere began to condense. Rain fell on Earth for the first time, not a gentle shower, but a torrential downpour that may have lasted for thousands or even millions of years. Water that had been locked in rock, water that had traveled from the outer solar system on comets, now fell from the sky in an endless storm, pooling in the low places, filling every depression and crater. The first oceans formed. At first, they may have been hot, nearly boiling from the heat still radiating from the surface. But gradually, over more millions of years, they cooled, the sky cleared, and for the first time in Earth's young existence, sunlight touched liquid water, creating reflections, ripples, and waves. This was the world the moon saw when it looked down, no longer a glowing ball of magma, but a dark sphere with the first hints of blue. Continents had not yet formed. Life had not yet stirred. But the stage was set. The pieces were in place. And Earth had survived its violent birth to become something new in the cosmos. A water world with a large moon spinning in the perfect distance from a stable star. Earth's story might have ended in desolation, another lifeless rock orbiting an ordinary star. But something extraordinary happened, something so precise it seems almost miraculous. Earth found itself in exactly the right place. A narrow band, a temperate zone where water could exist in all three forms: solid ice, liquid oceans, and vapor clouds all at once. This region is sometimes called the Goldilocks zone, after the fairy tale of the girl who found porridge that was neither too hot nor too cold, but just right. Scientists call it the habitable zone, the circumstellar habitable zone, or sometimes the life zone. Whatever name we give it, the concept is simple yet profound. There is a distance from every star where temperatures allow liquid water to persist on a planet's surface, and Earth orbits our Sun at precisely that distance. The numbers themselves seem unremarkable at first. Earth orbits the Sun at an average distance of about 150 million kilometers, a distance so common in astronomy that scientists use it as a standard unit of measurement, calling it 1 astronomical unit, or AU. But change that distance by even a small fraction, and everything transforms. If Earth were just 5% closer to the Sun, about 7.5 million kilometers nearer, the additional solar radiation would trigger a runaway greenhouse effect. The oceans would begin to evaporate more rapidly, filling the atmosphere with water vapor. Water vapor is itself a powerful greenhouse gas, trapping even more heat, which would cause even more evaporation. This feedback loop would continue until the oceans boiled away entirely, leaving Earth as Venus is today, a scorched world beneath clouds of sulfuric acid, with surface temperatures hot enough to melt lead. Move Earth 5% farther from the Sun, and the opposite occurs. With less solar energy reaching the surface, temperatures would drop. More water would freeze into ice, and ice reflects sunlight rather than absorbing it, a quality called albedo. The more ice that formed, the more sunlight would be reflected, causing temperatures to fall further. This feedback loop, the ice albedo feedback, could plunge Earth into a permanent snowball state, frozen from pole to equator, with ice kilometers thick covering the oceans. But Earth sits neither too close nor too far. It rests in the gentle middle, where water dances between its three phases, where ice caps glisten at the poles while liquid oceans cover most of the planet, and where clouds drift through the atmosphere carrying moisture from sea to land. This balance makes everything else possible. The distance alone, however, is not enough to explain Earth's perfect conditions. Mars orbits at 1.5 AU, just outside what scientists consider the habitable zone's inner edge. It is cold, but not impossibly so. Ancient Mars had liquid water on its surface. Dried riverbeds and lake deposits prove this. Yet today, it is a frozen desert, its atmosphere stripped away by solar wind, its water locked in ice beneath the surface or lost to space. Distance matters, but so does everything else about a planet. Earth benefits from something Mars lacks: the right mass. Our planet is large enough that its gravity can hold on to an atmosphere, creating a protective blanket of gases that trap heat and shield the surface. This is the greenhouse effect, and while it has become associated with climate concerns, it is also the reason Earth is habitable at all. Without any greenhouse effect, Earth's average temperature would be about negative 18 degrees Celsius, well below the freezing point of water. Instead, our atmosphere warms the surface to a comfortable average of about 15 degrees Celsius. The composition of that atmosphere is crucial. Earth's air is 78% nitrogen, 21% oxygen, and about 1% other gases, including the trace amounts of carbon dioxide, methane, and water vapor that create the greenhouse effect. This mixture is not arbitrary. It is the result of billions of years of geological and biological processes working together. Volcanoes release gases. Plants produce oxygen. Rocks weather and absorb carbon dioxide. Life and planet shape each other in an endless conversation. Our distance from the sun also determines how much energy Earth receives, and that energy drives everything we experience as weather and climate. The sun bathes Earth in about 1,361 watts of energy per square meter at the top of the atmosphere, a value called the solar constant, though it varies slightly with solar activity. Some of this energy is reflected back to space by clouds and ice. Some is absorbed by the atmosphere, and some reaches the surface, warming land and sea, driving winds and ocean currents, evaporating water that will later fall as rain. This incoming solar energy is distributed unevenly across Earth's surface, and that inequality creates motion. The equator, where the sun's rays strike most directly, receives far more energy than the poles, where sunlight arrives at a sharp angle and spreads across a larger area. This temperature difference between equator and poles drives the circulation of both atmosphere and oceans, creating the trade winds, the jet streams, the great ocean currents that ferry heat from hot regions to cold ones. And here, Earth's tilt enters the story once more. That 23.5-degree inclination, the result of the ancient collision that formed the moon, means that as Earth orbits the sun, different parts of the planet lean toward or away from our star during different times of the year. This creates the seasons: summer, when your hemisphere tilts toward the sun; winter, when it tilts away. Without this tilt, there would be no seasons, only a permanent climate zone dependent on latitude. The tropics would be slightly cooler, the poles slightly warmer, and life would be distributed very differently across the globe. The shape of Earth's orbit also matters. Unlike many planets, Earth's orbit is nearly circular. The distance between Earth and Sun varies by only about 3% throughout the year, from 147 million kilometers at perihelion in early January to 152 million kilometers at aphelion in early July. This consistency helps maintain stable temperatures. Some planets have highly elliptical orbits, swinging close to their stars and then far away, experiencing extreme variations in heating. Earth's near-circular path keeps our climate relatively steady. Even the timing of our orbit contributes to stability. Earth takes 365.25 days to complete one revolution around the Sun, our year. This duration is long enough to allow meaningful seasons, but not so long that summer and winter become extreme. Planets closer to the Sun orbit faster, with shorter years. Planets farther out take longer. Mars's year is 6 at 87 Earth days, for instance. Earth's year gives ecosystems time to adapt to seasonal changes without those changes being too abrupt or lasting too long. The relationship between Earth's rotation and orbit creates another perfect balance: the day-night cycle. Earth rotates once every 24 hours, giving most of the planet a regular rhythm of light and darkness. This cycle is slow enough that the side facing the sun doesn't overheat before rotating into shadow, and the night side doesn't freeze before rotating back into sunlight. Planets that rotate much faster or slower experience temperature extremes that make habitability difficult. Consider Venus again, Earth's closest planetary neighbor, often called Earth's twin because of similar size and mass. Venus orbits at 0.72 AU, only slightly closer to the sun than Earth. Yet it is utterly inhospitable. Its thick atmosphere, mostly carbon dioxide, creates a runaway greenhouse effect. Surface temperatures exceed 460 degrees Celsius, hot enough to melt lead. Atmospheric pressure at the surface is 92 times that of Earth, equivalent to being a kilometer underwater in Earth's oceans. And Venus rotates incredibly slowly, taking 243 Earth days to complete one rotation, meaning a Venusian day is longer than a Venusian year. The combination of proximity to the Sun and atmospheric composition has created hell. Mercury, even closer to the Sun, at 0.39 AU, shows us another extreme. With almost no atmosphere to distribute heat, the side facing the Sun reaches 430 degrees Celsius, while the night side plunges to negative 180 degrees Celsius, a temperature swing of more than 600 degrees. No liquid water could exist in such conditions. Life as we know it requires stability, and Mercury has none. Earth, by contrast, is a haven of moderation. Our distance from the Sun provides the right amount of energy. Our atmosphere distributes that energy and traps just enough heat. Our rotation gives us a rhythm of day and night that prevents extremes. Our tilt gives us seasons that drive mixing of atmosphere and oceans. Our nearly circular orbit keeps everything steady. Every factor works together, creating conditions where water stays liquid, where temperatures remain within a range that allows complex chemistry, where life can not only exist, but flourish. Scientists searching for life beyond Earth look for planets in the habitable zones of other stars. They have found thousands of exoplanets, worlds orbiting distant suns, and some indeed orbit in their stars' habitable zones. But distance alone does not guarantee habitability. A planet needs the right size to hold an atmosphere. It needs the right atmospheric composition to trap appropriate amounts of heat. It needs a magnetic field to protect that atmosphere from stellar wind. It needs tectonic activity to recycle carbon and regulate climate over geological time. It needs a large moon to stabilize its tilt. It needs, in short, to be Earth-like in dozens of subtle ways. This is what makes Earth so remarkable. Our planet is not special because it defies the laws of physics or chemistry. It is special because so many factors aligned in exactly the right way. The solar system formed with Earth in the Goldilocks zone. The collision with Theia gave us our tilt and our moon. Volcanic activity created an atmosphere. Gravity held that atmosphere in place. Life emerged and modified the atmosphere further. Plate tectonics continued to shape the surface. Every piece supports every other piece in a web of relationships billions of years old. When you step outside and feel the warmth of sunlight on your face, you are feeling the photons that traveled 150 million kilometers through the vacuum of space, arriving at Earth in exactly the right quantity to warm but not scorch, to illuminate but not blind. When you breathe, you draw in an atmosphere held in place by Earth's mass, its composition shaped by life itself, its temperature regulated by distance from our star. Earth's perfect distance is not just about numbers and orbits. It is about the gentle, persistent embrace of just right conditions that have lasted for billions of years. It is about finding yourself against all odds in exactly the place you need to be. It is about home and how rare and precious that home truly is in the vast, mostly hostile darkness of space. Above your head, stretching upward into the darkness of space, lies one of the most extraordinary and fragile things in the universe. A thin veil of air, so delicate, so impossibly thin, that if Earth were the size of an apple, our entire atmosphere would be no thicker than the fruit's skin. Everything that makes life possible, every breath you've ever taken, every word ever spoken, every bird that has ever soared through the sky, exists within this gossamer layer pressed against our planet by gravity's gentle hand. It is easy to forget how precious this blanket truly is. We move through it without thinking, invisible and ever present. Yet this thin shell of gases is all that stands between us and the lethal vacuum of space, between the warmth of sunlight and the absolute cold of the cosmos, between existence and oblivion. The atmosphere is not merely air, it is armor, it is sanctuary, it is the reason Earth glows blue and alive while every other world we've seen remains barren and still. The air you breathe right now is ancient beyond measure. Some of the nitrogen molecules entering your lungs may have drifted through the breath of dinosaurs, through the leaves of forests that turned to coal millions of years ago, through the first gasps of amphibians crawling onto primordial shores. The atmosphere remembers. It cycles endlessly, connecting every living thing across time, a shared inheritance passed down through eons. 78% nitrogen, 21% oxygen, and tiny traces of argon, carbon dioxide, and water vapor. This precise mixture, this delicate balance, emerged over billions of years through the patient work of geology and life itself. In Earth's earliest days, the atmosphere was nothing like the one we know. It was thick with carbon dioxide and water vapor, perhaps methane and ammonia, a toxic soup that would have suffocated any creature alive today. There was no oxygen to breathe, no ozone shield to block the sun's harshest rays. The young planet simmered beneath a heavy blanket of greenhouse gases, its surface still cooling from the violent collisions that built it. Lightning crackled through acidic clouds. Volcanoes exhaled vast plumes of gas that mingled with the churning air. It was a world raw and restless, still finding its chemical balance. Then, slowly, something miraculous began. Tiny organisms appeared in the oceans, simple bacteria that learned to harvest sunlight. These ancient microbes, the ancestors of all photosynthetic life, split water molecules and released oxygen as waste. At first, the oxygen didn't accumulate. It reacted immediately with iron dissolved in the seas, rusting away into the vast banded iron formations we mine today. For hundreds of millions of years, the ocean soaked up every molecule of oxygen, turning red with rust, while the atmosphere remained unchanged. But eventually, the seas became saturated. There was no more iron left to react. And then, finally, oxygen began to rise into the air. This transformation, called the Great Oxidation Event, fundamentally rewrote the planet's chemistry. It was perhaps the most important revolution in Earth's history, the moment when waste became breath, when poison became life. The oxygen accumulated slowly, one molecule at a time, building over millennia until it reached the levels we depend on today. That breathable air, the oxygen filling your lungs at this very moment, exists because billions of microscopic organisms labored for eons, transforming the atmosphere particle by particle. Every breath is a gift from the past, from life forms so small and ancient they seem like whispers in stone. The atmosphere arranges itself in layers, each with its own character and purpose, stacked like the pages of a book telling Earth's story at different altitudes. Closest to the surface lies the troposphere, where all weather happens, where clouds gather and rain falls, where winds blow and storms rage. This is the layer we inhabit, reaching upward about 12 kilometers at the equator, a bit less at the poles. Everything we call home, every mountain peak, every airplane flight, exists within this thin band of active air. Above it, temperature stops falling and begins to rise, marking the boundary called the tropopause, a ceiling beyond which weather cannot climb. Higher still stretches the stratosphere, a realm of stillness and clarity where the air thins to almost nothing. Here, between 15 and 50 kilometers above the surface, floats one of Earth's most important shields, the ozone layer. These molecules, each made of 3 oxygen atoms bound together, absorb the sun's ultraviolet radiation before it can reach the ground below. Without this invisible guardian, life as we know it could not exist on land. UV rays would burn through living tissue, shatter DNA, and turn the surface into a sterilized wasteland. The ozone layer is fragile, sensitive to chemicals we've released, yet it persists, quietly protecting everything beneath it. Commercial jets sometimes cruise at the bottom of the stratosphere, where the air is calm and thin, gliding through a layer that filters light itself. Beyond the stratosphere lies the mesosphere, the middle atmosphere, where temperatures plummet again to the coldest natural temperatures found anywhere on Earth. Here, meteors burn. When fragments of asteroids and comets plunge toward our planet at tens of thousands of kilometers per hour, they slam into the mesosphere's sparse molecules and ignite from friction. Most disintegrate entirely, vaporizing into bright streaks of light we call shooting stars. Every night, dozens of tons of cosmic debris rain down upon Earth, and nearly all of it is stopped here, turned to ash and vapor before it can threaten the surface. The mesosphere is our silent sentinel, standing watch against the cosmos. Higher still, the thermosphere begins, a layer so diffuse that it barely qualifies as atmosphere at all. Temperatures here can soar to over 1,000 degrees Celsius, though you would feel no heat because there are so few molecules to transfer energy. This is where the aurora dance, where charged particles from the sun collide with oxygen and nitrogen, painting the sky in curtains of green and red light. Satellites orbit through the thermosphere's lower reaches, skimming through wisps of atmosphere so thin they seem almost like space itself. The International Space Station circles here, still close enough to feel the faint drag of Earth's outermost air. Finally, at the very edge, the exosphere fades into the void. There is no clear boundary, no wall marking where Earth ends and space begins. The atmosphere simply thins, molecule by molecule, until individual atoms drift in the darkness, some escaping Earth's gravity entirely to join the solar wind. This gradual transition reminds us that our planet is not separate from space, but part of it, a world breathing out into the cosmos while gravity holds most of its air close. Yet the atmosphere alone is not enough to protect us. Beyond the air, invisible and vast, stretches another shield, the magnetosphere. Generated by the churning of molten iron deep within Earth's core, our planet's magnetic field extends tens of thousands of kilometers into space, deflecting the solar wind, a relentless stream of charged particles blasting outward from the sun at nearly 1 million kilometers per hour. Without the magnetosphere, this wind would strip away our atmosphere over millions of years, eroding it layer by layer until Earth became as barren as Mars. The red planet once had a thicker atmosphere, perhaps even liquid water on its surface, but its magnetic field weakened and died. The solar wind scoured its air away, leaving behind a cold, dry husk. Earth's magnetosphere wraps around us like an invisible cocoon, bending and channeling the solar wind around the planet. Sometimes, during powerful solar storms, the magnetosphere compresses and particles slip through at the poles, cascading down into the atmosphere to create the aurora. These light shows are beautiful, but they are also reminders of the violence happening just beyond our protective bubble. We live inside a magnetic fortress, shielded from forces that would unravel the very chemistry of life. The atmosphere also regulates temperature, creating the greenhouse effect that keeps Earth warm enough for liquid water. Certain gases, carbon dioxide, water vapor, methane, trap heat radiating from the surface, preventing it from escaping into space. Without this natural greenhouse, Earth's average temperature would plummet to well below freezing, and oceans would turn to ice. Too much greenhouse effect, however, and the planet becomes an oven, like Venus, where surface temperatures can melt lead. Earth's atmosphere maintains a delicate balance, absorbing just enough heat to sustain life without cooking it. For billions of years, geological and biological processes have worked together to keep this balance stable, adjusting gas concentrations as continents drift and life evolves. Even the weight of the atmosphere is extraordinary. At sea level, the air presses down upon us with a force of about 1 kilogram per square centimeter. We don't feel it because the pressure inside our bodies matches the pressure outside. But this invisible weight is what allows us to breathe, pushing air into our lungs, keeping water liquid at room temperature, enabling sound to travel in waves through the air. Climb a mountain, and the pressure drops. There are fewer molecules above you, less weight pressing down. At the summit of Everest, the air pressure is only a third of what it is at sea level, so thin that most people cannot breathe without supplemental oxygen. Pilots and astronauts understand this viscerally. Rise too high without protection, and the air becomes too thin to sustain life. This thin shell of atmosphere is all that allows Earth to be a living world. It scatters light to paint our skies blue, burns meteors before they strike, shields us from radiation, holds in warmth, and provides the very gases we need to exist. It is the most precious boundary in the solar system, a miracle of chemistry and physics that emerged from chaos and has persisted for billions of years. Now, breathe slowly Feel the air move in and out of your chest. The atmosphere breathes with you, holding you close, protecting you from the cold darkness beyond, a gentle blanket wrapped around the only home we've ever known. What makes our planet unique in the solar system is water. 71% of Earth's surface lies beneath oceans, seas, lakes, and rivers. Water dominates our world so completely that calling it Earth feels almost like a mistake. Perhaps it should have been called ocean instead. Water is everywhere. It fills the vast Pacific basin, stretching nearly halfway around the globe. It carves through mountain valleys as rivers. It freezes into polar ice caps miles thick. It rises as vapor into clouds, falls as rain upon forests, seeps into soil, and flows through underground aquifers hidden from sight. Water moves constantly, endlessly cycling between ocean and sky and land, never resting, never still. Every drop you've ever drunk, every tear you've ever cried, every cell in your body filled with liquid is part of this ancient cycle. The same water that quenched the thirst of dinosaurs might someday fall as snow on a distant mountain, might flow through a river you've never seen, might evaporate from a tropical sea to become the cloud above your head tomorrow. The mystery of how water arrived on Earth is one that scientists have pondered for generations. In the planet's violent infancy, when the surface was molten and glowing red with heat, any water that existed would have boiled away into space. The young sun blazed intensely, and the inner solar system was too hot for ice to survive. Yet somehow, after Earth cooled, water appeared. Perhaps it was always here, trapped in the minerals of rocks that coalesced to form the planet, locked away in crystal structures deep underground. As the surface cooled and volcanoes erupted, these minerals released their water as steam, filling the skies with dense clouds that eventually condensed and fell as rain. Rain that didn't stop. Rain that fell for thousands, perhaps millions of years, slowly filling the low places, carving the first rivers, gathering into the first seas. Or perhaps water came from beyond. Comets, those icy wanderers from the outer reaches of the solar system, are mostly water ice mixed with rock and organic compounds. During the late heavy bombardment, a period roughly 4 billion years ago, when asteroids and comets pummeled the inner planets, countless impacts may have delivered oceans worth of water to Earth's surface. Each collision was catastrophic, releasing energy that vaporized rock and carved massive craters. Yet each also brought gifts: water, carbon, perhaps even the organic molecules that would eventually assemble into life. The evidence suggests both sources contributed. Water rose from within and rained down from above, gathering over eons until the planet gleamed blue. Today, the oceans hold an almost incomprehensible volume of water, more than 1.3 billion cubic kilometers of it, filling basins that plunge deeper than mountains rise tall. If you could gather all this water into a single sphere, it would measure about 1,400 kilometers across, a droplet large enough to dwarf continents, yet still small compared to the planet itself. Most of this water, 97%, is salt water, made undrinkable by dissolved minerals carried from rocks over billions of years. Rivers constantly erode stone, carrying ions of sodium, chloride, magnesium, and calcium toward the sea. The ocean has been accumulating these salts since it first formed, growing saltier with each passing millennium, though the process is so slow that its concentration has remained relatively stable for hundreds of millions of years. Only 3% of Earth's water is fresh, and most of that is locked away in ice. The vast ice sheets of Antarctica and Greenland hold nearly 70% of the world's fresh water, frozen into layers kilometers thick, some of it ice that fell as snow hundreds of thousands of years ago. If all this ice melted, sea levels would rise more than 60 meters, drowning coastlines and reshaping continents. The remaining fresh water exists in lakes, rivers, swamps, and underground aquifers, with only the tiniest fraction available at any moment for living things to drink. We exist on the thinnest margin of abundance, sustained by a resource that is everywhere, and yet, in its usable form, remarkably scarce. But water does not simply sit in oceans and ice caps. It moves. The water cycle is one of Earth's great engines, a perpetual motion machine driven by the sun's energy. Every year, the sun's warmth evaporates roughly 505,000 cubic kilometers of water from oceans, lakes, and soil. That water rises as invisible vapor, lighter than air, drifting upward into the atmosphere where cooler temperatures cause it to condense into clouds. Wind carries these clouds across continents, over mountains, above forests and deserts. When conditions align, the vapor condenses further, forming droplets heavy enough to fall. Rain returns to the surface, landing on leaves, soaking into earth, trickling into streams that merge into rivers that flow inevitably back to the sea. The cycle completes and begins again, endlessly. This constant movement distributes heat around the planet. When water evaporates, it absorbs energy, cooling the surface. When it condenses high in the atmosphere, that energy is released as warmth, driving winds and weather systems. Tropical oceans are vast solar collectors, absorbing sunlight and transferring it through evaporation to distant places. Hurricanes are born from this process, spinning storms powered by the temperature difference between warm water and cool air. The water cycle connects every part of Earth's surface, carrying not just moisture, but energy, nutrients, and even life itself. Seeds drift on rivers. Birds follow seasonal rains. Entire ecosystems pulse with the rhythm of wet and dry, flood and drought, the heartbeat of water moving through the world. Beneath the surface, the oceans hide wonders and mysteries. The average depth is about 3,700 meters. But in places, the seafloor plunges into trenches that descend more than 11 kilometers, deeper than mountains are tall. These abyssal plains are realms of eternal darkness and crushing pressure, cold and still, yet inhabited by strange creatures adapted to extremes. Sunlight cannot penetrate beyond a few hundred meters, so the deep ocean exists in permanent night, illuminated only by the bioluminescence of organisms that have learned to make their own light. Down there, the pressure is so immense that it would crush a human instantly. Yet life persists. Translucent fish, giant squid, fields of tube worms clustering around hydrothermal vents where superheated water erupts from cracks in the ocean floor. The oceans are not uniform. Currents flow through them like rivers within rivers, massive streams of water circulating across entire ocean basins. Warm currents carry heat from the equator toward the poles, while cold currents return the flow, moderating global temperatures. The Gulf Stream, for instance, moves more water than all the world's rivers combined, flowing from the Caribbean up the eastern coast of North America and across the Atlantic toward Europe. Without it, Britain and Scandinavia would be far colder, their climates more like those of Labrador or Siberia at similar latitudes. Ocean currents are driven by wind, by differences in temperature and salinity, by the rotation of the Earth itself. They shape weather patterns, influence marine life, and connect distant shores in a global circulation that has flowed for millions of years. Yet water exists not only on the surface and in the air. Deep beneath the crust, locked within the crystal structures of minerals, lies perhaps as much water as fills all the oceans above. This hidden reservoir was discovered only recently through the study of rare minerals brought to the surface by volcanic eruptions. Ringwoodite, a high-pressure form of olivine found in the mantle's transition zone hundreds of kilometers down, can contain water molecules trapped within its atomic lattice. Geologists now believe the mantle holds vast quantities of water, not as liquid, but as hydroxyl ions bound into rock. If released, this subterranean ocean could flood the surface many times over. But it remains locked away, cycling slowly through the mantle as tectonic plates descend into subduction zones, carrying water-rich minerals deep into the earth where they melt and rise again through volcanoes, completing a cycle that takes millions of years. This deep water cycle may be essential to Earth's long-term habitability. By regulating how much water remains at the surface, the mantle acts as a reservoir and buffer, preventing oceans from either evaporating entirely or flooding the continents. Water carried into the mantle at subduction zones reduces melting temperatures, helping to generate the magma that builds volcanic arcs and new crust. Water released by volcanic eruptions replenishes the surface, replacing what is lost to space or locked in minerals. This exchange between surface and interior has maintained Earth's oceans for billions of years, a balance between burial and release that keeps the planet neither too wet nor too dry. The presence of liquid water is perhaps the single most important factor that makes Earth suitable for life. Water is an extraordinary molecule. Two hydrogen atoms bonded to one oxygen atom create a substance with unusual properties. It expands when it freezes, causing ice to float rather than sink, insulating the liquid water beneath and allowing life to survive in frozen lakes and polar seas. It has a high heat capacity, meaning it can absorb and release vast amounts of energy without changing temperature drastically, stabilizing climates. It is an excellent solvent, able to dissolve more substances than nearly any other liquid, allowing complex chemistry to occur within cells. Life as we know it requires liquid water. Every organism on Earth, from bacteria to blue whales, depends on it. DNA, proteins, the membranes that enclose cells, all function only in water's presence. Scientists searching for life beyond Earth focus on finding liquid water. The icy moons of Jupiter and Saturn, Europa, Enceladus, may hide vast oceans beneath their frozen crusts, kept liquid by tidal heating. If water exists there, perhaps life does too. Mars once had rivers and lakes. Their dry channels still scar the surface. Where the water went, into ice, into the ground, lost to space, remains one of the red planet's great mysteries. Earth's abundance of liquid water, stable for billions of years, is a rarity, a stroke of fortune that arose from our distance from the sun, our planet's size and gravity, and the presence of an atmosphere to hold water vapor close. This combination, so essential and yet so specific, may be uncommon in the universe. We float on a water world, rare and precious, a blue oasis in the vastness of space. Your body is roughly 60% water by weight. Every cell, every tissue, every organ relies on it. Water carries nutrients through your bloodstream, cushions your brain, lubricates your joints, regulates your temperature through sweat. The water inside you right now has been part of the cycle for billions of years. It has fallen as rain on ancient seas, flowed through rivers that no longer exist, risen as vapor from tropical storms, frozen in glaciers, melted, and moved again. You are made of the same substance that fills the oceans, that carves canyons and nourishes forests. You are, quite literally, part of Earth's water, borrowed for a little while, held together by biology, soon to return to the cycle and continue the journey. The boundary between you and the ocean is temporary. The water that sustains you is the same water that has always sustained everything, flowing endlessly, connecting all life across time in one vast, patient circulation. From the window of a spacecraft, Earth does not appear as a globe of rock or a sphere of stone. It appears as a painting, a masterpiece of color suspended against the infinite black of space, swirling with blues and whites, brushed with greens and browns, capped with brilliant white at the poles. The astronauts who first saw our planet from this distance were moved to silence, to tears, to poetry. They had expected a world, but what they found was beauty, a fragile ornament of color hanging in the void, so vivid and alive that it seemed impossible anything else in the universe could compare. They called it the blue marble, and the name has stayed because nothing else captures that first impression. A sphere of liquid light glowing softly in the darkness. The blue is what strikes you first. It dominates everything, washing across more than 2/3 of the visible surface. This is the blue of water, of oceans stretching across vast basins, absorbing and reflecting sunlight in a way that no other substance quite manages. Water is transparent, nearly colorless in small quantities, yet it absorbs the red wavelengths of light more readily than the blue. When sunlight penetrates the ocean, red light is absorbed within the first few meters, orange and yellow slightly deeper, until only blue remains to scatter back toward space. The deeper the water, the richer the blue becomes. Stand on a beach, and the shallows appear turquoise, tinged with green from sediment and algae. But look toward the horizon, where the ocean drops away into abyssal depths, and the color deepens to a profound, almost violet blue, the color of distance and mystery. This blue is Earth's signature. No other planet in the solar system wears it. Venus is shrouded in pale yellow clouds of sulfuric acid. Mars glows rusty red from iron oxide dust covering its deserts. Jupiter and Saturn swirl with bands of brown, white, and amber, storms the size of planets churning through their thick atmospheres. But Earth alone is blue, and that blueness announces the presence of liquid water, the substance that makes life possible. If an alien astronomer observed our solar system from light years away, the blue-green tint of Earth would immediately mark it as different, as potentially habitable, as worth a closer look. Yet the blue is not only in the water. The sky itself is blue, and for a different reason entirely. When sunlight enters the atmosphere, it collides with molecules of nitrogen and oxygen. These molecules are far smaller than the wavelengths of visible light, and when light strikes them, it scatters in all directions. This scattering, called Rayleigh scattering after the physicist who explained it, affects shorter wavelengths more strongly than longer ones. Blue light, with its short, energetic waves, scatters much more readily than red light. So as sunlight travels through the air, blue light bounces from molecule to molecule, spreading across the entire sky. No matter where you look, east, west, up, or down, blue light reaches your eyes from every direction. The sky becomes a dome of scattered blue, a ceiling of color painted by physics. The sun itself appears yellow or white because we see it through this scattering atmosphere. The blue light has already been deflected away, leaving the warmer tones to travel straight to our eyes. But if you could see the sun from space beyond the atmosphere's interference, it would appear almost pure white, a blazing sphere emitting all wavelengths of visible light in roughly equal measure. The colors we associate with sky and sun are artifacts of our atmosphere, gifts of the air that wraps around us. Other worlds with thinner atmospheres, or atmospheres of different composition, would paint their skies in different hues. On Mars, where the air is thin and filled with fine dust, the sky glows a pale butterscotch during the day, and the sunsets are blue, the opposite of Earth. Because here, on our world, sunsets are red. As the sun drops toward the horizon, its light must travel through a much greater thickness of atmosphere to reach your eyes. The extra distance means even more scattering. By the time sunlight has passed through hundreds of kilometers of air, nearly all the blue light has been scattered away in other directions. What remains are the longer wavelengths, orange, red, deep crimson. These colors pour across the sky in waves, painting clouds from below, turning the horizon into fire. Sunsets are daily reminders of the atmosphere's presence, of the way light bends and breaks as it passes through layers of air. Ancient peoples saw omens in red skies. Poets wrote of them as symbols of endings and transitions. But they are simply physics, the same Rayleigh scattering that makes the sky blue, now revealing the colors that survive the longest journey through the air. From space, other colors emerge. Green swaths of tropical rainforests stretch across equatorial regions, so dense with vegetation that they are visible from orbit. The Amazon basin, the Congo, the forests of Southeast Asia all appear as verdant patches on the planet's face, unmistakable signs of life. This green comes from chlorophyll, the molecule that captures sunlight for photosynthesis, the process that turns light into life. Chlorophyll absorbs red and blue wavelengths, but reflects green, giving plants their characteristic color. The green of Earth's forests is not a mere aesthetic detail. It is evidence of biology at work, of countless organisms converting solar energy into the sugars and starches that fuel the food web. Without this green, without the plants that perform the quiet alchemy of photosynthesis, the oxygen in our atmosphere would slowly dwindle, and the intricate ecosystems we depend on would collapse. Even the oceans reveal shades of green in certain places. These are phytoplankton blooms, vast floating meadows of microscopic algae drifting near the surface. Phytoplankton are tiny, individually invisible, but when they bloom in huge numbers, they tint the water green or turquoise, sometimes even red or brown, depending on the species. These blooms can cover areas larger than countries, visible from satellites as swirling clouds of color drifting through the blue. Phytoplankton are among the most important organisms on Earth. They produce between 50 and 80% of the planet's oxygen, more than all the forests combined. Every other breath you take comes from these microscopic plants floating in the sea. They form the base of the ocean food web, feeding everything from tiny krill to the largest whales. Their presence is so significant that scientists can track ocean health and climate patterns by monitoring bloom activity from space. White dominates the poles. Ice and snow, reflecting nearly all the sunlight that strikes them, create brilliant caps at the top and bottom of the world. Antarctica, larger than the United States, is covered by an ice sheet averaging more than 2 kilometers thick in places. Greenland, though smaller, holds enough ice that if it melted entirely, sea levels would rise more than 7 meters. These white expanses are Earth's refrigerators, helping to regulate global temperatures by reflecting solar energy back into space. The more white ice exists, the more sunlight is bounced away, keeping the planet cooler. This is called the albedo effect, and it creates a feedback loop. Ice reflects light, which keeps temperatures low, which preserves the ice. But if ice melts and reveals darker ocean or land beneath, more sunlight is absorbed. Temperatures rise, and more ice melts. The balance is delicate, sensitive to even small changes in climate. Clouds, too, are white, or shades of gray when thick with moisture. They swirl across the planet in patterns shaped by wind and weather, clustering along the equator where heat drives convection, spinning into hurricanes and typhoons, stretching into thin wisps at high altitudes. Clouds are made of water droplets or ice crystals suspended in air, each particle tiny enough to scatter all wavelengths of visible light equally. That's why clouds appear white. They scatter all colors together, reflecting sunlight in a blend that our eyes perceive as pure white. Darker clouds look gray because they are so thick that light cannot penetrate deeply. The bottom layers remain in shadow, even while the tops shine brightly. From space, these swirling white patterns give Earth a dynamic, ever-changing face. No photograph taken today will match one taken tomorrow. The clouds shift, the weather evolves, and the planet wears a new expression with each passing hour. Deserts contribute their own palette. The Sahara visible as a vast tan expanse across northern Africa, reflects the colors of sand and stone, iron-rich minerals oxidized over millennia into shades of gold, ochre, and rust. The Australian outback glows red from ancient soils weathered under relentless sun. The deserts of Arabia and the Gobi add lighter tones, almost white in places where salt flats or gypsum deposits cover the ground. These arid lands, though harsh and seemingly lifeless from a distance, are part of Earth's color spectrum, proof that not all the planet is blue and green. Dust storms occasionally lift material from these deserts high into the atmosphere, and winds carry it across oceans. Saharan dust has been found in the Amazon, in the Caribbean, even in Europe, linking ecosystems across thousands of kilometers. The colors of Earth are not isolated but connected, carried by wind and water in a global exchange. Even from space, cities are beginning to show, especially at night when artificial lights trace the outlines of coasts and continents. These lights are a new color, a human color, marking our presence with tiny dots and lines that spread like networks across the dark side of the planet. During the day, urban areas appear as gray smudges, their concrete and asphalt absorbing and reflecting light differently than natural landscapes. From orbit, you can see the environmental impact of humanity. Deforested patches, reservoirs filling valleys, the grid patterns of agriculture spreading across plains. Earth is no longer a purely natural canvas. We have added our marks, for better and worse, changing the colors and textures visible from space. But the overwhelming impression, even now, is of a living world. The colors of Earth are not static like those of lifeless worlds. They shift with seasons. In autumn, temperate forests blaze with reds and golds as leaves change before falling. In spring, greens return with new growth. Ice advances and retreats with the rhythm of centuries. Oceans churn with currents that bring cold, nutrient-rich water to the surface, triggering blooms that paint the sea. Volcanic eruptions add plumes of gray ash. Forest fires send smoke across continents. Even the atmosphere itself changes color at the edges, fading from deep blue near the surface to pale azure higher up, and finally to the black of space. There is no hard line, no clear boundary, just a gradual transition where air gives way to void. These colors tell stories. The blue speaks of water, of oceans that have existed for billions of years. The green announces life, photosynthesis, the presence of organisms transforming light into energy. The white marks ice and cloud, the cycling of water between surface and sky. The browns and golds reveal land, continents shaped by tectonics and erosion. Together, they create a portrait of a planet in balance, where geology, atmosphere, ocean, and life interact in complex, beautiful ways. Earth's colors are not accidents. They are the visible consequences of physical and chemical processes honed over eons. The outward expression of a world that has found, against all odds, a stable configuration where liquid water, breathable air, and abundant life can coexist. This is the only world we know that looks like this, the only one painted in these particular shades. Every color you've ever seen, every sunset and forest and ocean wave, exists because Earth is positioned just right, shaped just so, alive in just this way. The blue marble turns slowly in the darkness, casting its colors into the void, a beacon of complexity and beauty in a universe that is mostly empty and cold. And you are part of that blue marble. Earth is not merely a planet of rock and water, wind and ice. It is a living world, and the variety of life it hosts is almost beyond comprehension. Everywhere you look, in every ocean, on every mountain, beneath every stone, life has found a way to establish itself, to adapt, to thrive. From the deepest ocean trenches to the highest peaks, from scorching deserts to frozen poles, from boiling hot springs to the dark caves miles underground, life persists. This abundance, this extraordinary variety of living things, is what scientists call biodiversity. And Earth possesses it in such richness that we have not yet finished counting all the forms it takes. Scientists estimate that there are approximately 8.7 million species of plants, animals, fungi, and microorganisms living on Earth today. This is only an estimate because we have not discovered them all. In fact, we have formally described and named only about 1.2 million species. The rest, more than 80%, remain unknown to science, living their lives in remote forests, in the deep ocean, in soil beneath our feet, undiscovered, uncatalogued, quietly going about the business of existence. Think about that for a moment. 8.7 million different kinds of life, each one unique, each one the result of billions of years of evolution, shaped by its environment, adapted to its particular way of living. Each one connected to countless others in webs of relationship so complex that we are still trying to understand how they all fit together. Consider insects alone. There are likely more than 1 million species of insects, making them the most diverse group of animals on Earth. Beetles comprise perhaps 400,000 species, more species of beetle than all species of plants combined. In a single rainforest tree, you might find hundreds of species of insects, many of them found nowhere else on Earth. Some live only on that particular species of tree, eating only its leaves or pollinating only its flowers, their entire existence bound to one plant in one forest. And insects are only one group among many. There are approximately 10,000 species of birds, ranging from the tiny bee hummingbird, weighing less than 2 grams, to the enormous ostrich, standing more than 2 meters tall. There are around 16,500 species of mammals, from shrews you could hold on your thumb to blue whales longer than a basketball court. There are more than 10,000 species of reptiles, over 8,000 species of amphibians, and perhaps 35,000 species of fish. Plants, too, show staggering diversity. Scientists have described about 400,000 species of plants, from tiny mosses to massive sequoia trees that can live for thousands of years and grow taller than a 25-story building. Each plant species has its own way of capturing sunlight, its own strategy for reproduction, its own relationship with pollinators, seed dispersers, herbivores, and the soil beneath its roots. Fungi deserve special mention, for they are often overlooked yet crucial to nearly every ecosystem on Earth. There may be 2 to 5 million species of fungi, though we have identified only about 150,000. Fungi decompose dead material, returning nutrients to the soil. They form partnerships with plant roots called mycorrhizae, helping plants absorb water and minerals in exchange for sugars. Some fungi can break down toxic pollutants. Others produce the antibiotics that revolutionized medicine. The largest living organism on Earth is a fungus, a honey mushroom in Oregon, whose underground network stretches across 10 square kilometers and may be thousands of years old. But the true abundance of life exists at scales too small to see. Microorganisms, bacteria, archaea, protists, and viruses vastly outnumber all visible life. In a single gram of soil, there may be 10 billion microorganisms representing thousands of species. In your body right now, there are more bacterial cells than human cells. Your skin, your mouth, your gut, all host complex communities of microbes, many of which help keep you healthy. The ocean contains countless microorganisms, including phytoplankton that produce more than half of Earth's oxygen through photosynthesis, making every other breath you take a gift from microscopic organisms drifting in sunlit waters. Life has colonized virtually every environment Earth offers. In the driest deserts, where decades may pass without rain, specialized plants and animals wait, dormant, for the rare storms that allow them to briefly flourish. Seeds can lie dormant for years. Spadefoot toads burrow underground and seal themselves in mucus cocoons, waiting for rain. When storms finally come, the desert explodes with life. Flowers bloom within days. Insects emerge. Toads reproduce frantically in temporary pools before everything dries again. In the coldest places, life adapts to ice and snow. Emperor penguins breed in Antarctica during winter, when temperatures drop below -40 degrees Celsius and winds exceed 150 kilometers per hour. Arctic wolves and polar bears hunt on sea ice. Tiny organisms called tardigrades, or water bears, can survive being frozen for decades. Some bacteria in Antarctic ice have been dormant for hundreds of thousands of years, yet can still be revived. At the other extreme, life thrives in environments so hot they would kill most organisms instantly. Thermophiles, heat-loving microbes, live in hot springs where water temperatures exceed 80 degrees Celsius. In Yellowstone's Grand Prismatic Spring, bacteria create rainbow colors in water, so hot a human would die in seconds. Near deep-sea hydrothermal vents, where superheated water gushes from the sea floor, entire ecosystems exist in complete darkness, feeding not on sunlight, but on chemical energy from Earth's interior. Life has even colonized extreme depths. The Mariana Trench, nearly 11 kilometers below the ocean surface, hosts fish, amphipods, and bacterial communities living under pressure more than 1,000 times atmospheric pressure at sea level. These creatures have adapted to darkness, cold, and crushing pressure that would instantly kill surface-dwelling organisms. Some have transparent bodies. Others produce light through bioluminescence, carrying their own illumination through the perpetual night of the deep ocean. Underground, too, life flourishes in places we might think barren. Deep caves, sealed from sunlight for millions of years, contain unique species that have lost their eyes and pigmentation, navigating by touch and chemical sensing. Even deeper, in cracks and rock kilometers below the surface, bacteria live in hot, mineral-rich water, metabolizing compounds like hydrogen and methane, forming an entirely separate biosphere we barely understand. This ability of life to colonize extreme environments suggests something profound. Life is not fragile. It is resilient. It is creative. Once it establishes itself, it finds ways to persist, to adapt, to spread into every available niche. Given water, energy, and time, life discovers solutions to seemingly impossible challenges. The distribution of life across Earth is not random. Certain regions contain far more species than others. These biodiversity hotspots are areas with exceptional concentrations of endemic species, species found nowhere else. Tropical rainforests, though covering only about 6% of Earth's land surface, contain more than half of all terrestrial species. A single hectare of rainforest in Ecuador might contain more species of trees than exist in all of North America. The coral reefs, sometimes called the rainforests of the sea, occupy less than 0.1% of the ocean floor, yet host about 25% of all marine species. Madagascar, an island that separated from Africa millions of years ago, evolved in isolation and now hosts species found nowhere else. Lemurs, strange chameleons, bizarre insects. About 90% of Madagascar's wildlife is endemic. Australia, isolated by ocean for tens of millions of years, developed its own unique fauna. Marsupials like kangaroos and koalas, the egg-laying platypus and echidna, and thousands of unique plant species. Islands, in general, are engines of biodiversity. The Galapagos Islands, where Darwin observed the finches that helped inspire his theory of evolution, host many endemic species. Hawaii, the most isolated major island chain on Earth, developed unique birds, plants, and insects that evolved from the few species that managed to colonize these remote volcanic islands. Each island can have its own unique species, adapted to its particular environment. But biodiversity is not only about the number of species, it is also about genetic diversity within species and about the diversity of ecosystems themselves. Genetic diversity is crucial for species survival. It provides the raw material for adaptation to changing conditions. A species with low genetic diversity is vulnerable to disease, environmental change, and extinction. High genetic diversity gives populations resilience, the ability to respond to challenges. Ecosystem diversity matters too. Earth contains many types of ecosystems, each functioning differently. Tropical rainforests cycle nutrients rapidly in thin soils, with most nutrients locked in living biomass. Temperate forests experience seasonal changes, with trees dropping leaves that decompose over winter, building rich soil. Grasslands support large herds of grazing animals. Wetlands filter water and provide nurseries for fish. Each ecosystem type provides different services, supports different species, and contributes to the overall functioning of the biosphere. These ecosystems are connected in ways we are still discovering. A forest in Africa influences rainfall patterns across the continent. Phytoplankton blooms in polar seas affect the amount of carbon dioxide in the atmosphere worldwide. Migratory birds connect ecosystems across hemispheres, carrying nutrients from winter grounds to breeding areas. Salmon swim from the ocean into rivers, bringing marine nutrients into freshwater and forest ecosystems. Everything is linked. Nothing exists in isolation. Within ecosystems, species interact in countless ways. Predators hunt prey, keeping populations in balance. Herbivores eat plants, which respond by evolving defenses. Pollinators visit flowers, transferring pollen in exchange for nectar. Decomposers break down dead matter, recycling nutrients. Parasites live on or in hosts. Mutualists help each other, like clownfish sheltering in sea anemones, protecting them from predators while gaining protection from the anemone's stinging cells. These relationships create food webs of stunning complexity. Energy from the sun is captured by plants through photosynthesis. Herbivores eat plants, carnivores eat herbivores, and top predators eat other carnivores. But the web is far more intricate than this simple chain suggests. Most animals eat many different foods. Most plants are eaten by many different herbivores. Remove one species, and the effects ripple through the entire web, sometimes in unexpected ways. This interconnectedness means that biodiversity is not just about individual species, but about relationships. A rainforest is not simply a collection of species that happen to live in the same place. It is a community of organisms that have co-evolved over millions of years, each depending on others in ways both obvious and subtle. The fig tree depends on a specific species of wasp to pollinate it. The wasp depends on the fig. Many birds and mammals depend on figs for food. Predators depend on those fruit eaters. The entire ecosystem is woven together by threads of dependence and interaction. Earth's biodiversity is the result of nearly 4 billion years of evolution. Life began as single cells in ancient oceans. Over unimaginable stretches of time, it diversified. Some cells learned to photosynthesize, creating their own food from sunlight. Others formed cooperative colonies that eventually became multicellular organisms. Life moved from sea to land about 450 million years ago. Plants colonized the continents, followed by arthropods and vertebrates. Each group diversified, adapted, experimented with new forms and strategies. Mass extinctions periodically wiped out large portions of life, but each time, the survivors diversified to fill empty niches. After the extinction that ended the dinosaurs' reign 66 million years ago, mammals diversified explosively, evolving from small, shrew-like creatures into the incredible variety we see today. Whales in the ocean, bats in the air, countless forms on land. Birds, descendants of dinosaurs, diversified into 10,000 species. Each lineage tells a story of adaptation, of response to changing environments, of opportunity seized when competitors disappeared. Humans are latecomers to this grand pageant of life. Yet in the brief time, we have had enormous impact. We have altered landscapes, domesticated plants and animals, and spread to every continent. Our activities now influence the climate, the chemistry of the ocean, and the survival of countless other species. We live in what many scientists call the sixth mass extinction, driven not by asteroids or volcanoes, but by human activity, habitat destruction, pollution, Climate change, overhunting, and introduction of invasive species are causing species to disappear at rates perhaps 1,000 times faster than the natural background rate. We may be losing dozens of species per day, many of them vanishing before we even know they existed. Yet this same species that causes such disruption is also capable of understanding and valuing biodiversity. We can study ecosystems, recognize our dependence on them, and work to protect what remains. We are beginning to understand that biodiversity is not merely decorative, it is functional. Diverse ecosystems are more productive, more stable, more resilient to disturbance. They provide services we depend on: clean water, breathable air, pollination of crops, decomposition of waste, regulation of climate, protection from storms and floods. In fact, in the vast sweep of Earth's 4.54 billion year history, humans have existed for only the briefest moment. If you could compress all of Earth's time into a single 24-hour day, with the planet forming at midnight, humans would appear at approximately 11:59:58 p.m., just 2 seconds before the clock strikes midnight again. We are newcomers, latecomers, to a world that has been spinning through space, evolving and transforming for eons beyond our comprehension. Yet in our brief tenure here, we have become something unprecedented, a species aware of its own existence, capable of wondering about its place in the cosmos, able to look back across time and understand the story of the world that made us. Homo sapiens, our species, emerged in Africa approximately 300,000 years ago. This is a blink in geological time, barely registering on the scale of Earth's grand processes. When our earliest ancestors first walked upright, the mountains and valleys they traversed were essentially the same as today. The stars they looked up at were arranged in nearly the same constellations. The seasons turned in the same rhythm. Earth did not notice our arrival. The continents continued their slow drift. Volcanoes erupted. Rivers carved canyons. Life evolved and adapted, as it had for billions of years before we came. But those early humans were different from any species that had come before. They had large brains capable of abstract thought, language, planning for the future. They could communicate complex ideas, pass knowledge from generation to generation, work together in ways that transcended instinct. They could look at their world and ask why. Why does the sun rise? Where do we come from? What lies beyond the horizon? For most of our species' existence, humans lived as nomadic hunter-gatherers, moving with the seasons, following herds of animals, gathering plants and fruits as they ripened. Our numbers were small, perhaps a few million individuals scattered across Africa. We were part of the ecosystem, one species among millions, subject to the same forces of predation, disease, and environmental change as any other animal. We hunted, but we were also hunted. We gathered food, but sometimes food was scarce. We were constrained by our environment, shaped by it, adapted to it. Then, about 70,000 years ago, something remarkable happened. A small group of humans, perhaps only a few thousand individuals, left Africa. They crossed into the Middle East, then spread outward in waves across the entire world. They moved through Asia, reaching Australia by about 50,000 years ago. They crossed into Europe, displacing the Neanderthals who had lived there for hundreds of thousands of years. They reached the Americas, crossing a land bridge that appeared during ice ages when sea levels dropped, arriving by at least 15,000 years ago and possibly much earlier. This migration was one of the most extraordinary journeys in the history of life. Humans, who had evolved in the warm savannas of Africa, found ways to survive in every climate Earth offers. In the Arctic, they learned to hunt seals and build shelters from ice. In deserts, they found water sources and adapted to extreme heat. In mountains, they thrived at altitudes where oxygen is thin. On islands, they became skilled navigators, crossing vast stretches of open ocean in simple boats. No other large mammal has colonized so much of the planet so quickly. By 10,000 years ago, humans lived on every continent except Antarctica. They had adapted to rainforests and tundra, coasts and inland plains, islands and mainlands. They spoke thousands of languages, developed different cultures, created art and music and stories that explained their world. And everywhere they went, they changed their environment. They used fire to manage landscapes, burning forests to encourage new growth that would attract game animals. They hunted large animals, and many of those animals, mammoths, giant ground sloths, enormous flightless birds, went extinct soon after humans arrived. Then came the most transformative change in human history: agriculture. About 10,000 to 12,000 years ago, independently in several regions around the world, humans began to domesticate plants and animals. Instead of following wild herds, they kept sheep, goats, cattle, and pigs. Instead of gathering wild grains, they planted seeds and harvested crops. This shift from nomadic hunting and gathering to settled farming is called the Neolithic Revolution, and it changed everything. Agriculture allowed human populations to grow dramatically. A plot of farmed land can support far more people than the same area of wilderness. Villages grew into towns, towns into cities. With surplus food, not everyone needed to farm. Some people became craftsmen, making pottery, tools, and cloth. Others became traders, priests, soldiers, administrators. Complex societies emerged, with hierarchies and specialization of labor. Writing was invented to keep records. Mathematics developed to measure fields and predict harvests. Civilization, as we understand it, began. But agriculture also bound humans more tightly to the land. Farmers must stay in one place, tending their crops through the growing season. They depend on good weather, adequate rainfall, healthy soil. When harvest failed, people starved, and clearing land for farming meant cutting down forests, draining wetlands, diverting rivers. For the first time, humans began to reshape landscapes on a large scale, transforming wilderness into farmland, converting diverse ecosystems into monocultures of wheat, rice, or corn. As populations grew and societies became more complex, human impact on Earth accelerated. Forests were cleared for timber and farmland. Rivers were dammed and channeled for irrigation. Mines were dug to extract metals. Cities expanded, covering the land with stone and brick. Roads connected settlements, facilitating trade and the movement of armies. Empires rose and fell, each leaving its mark on the landscape. Yet for most of human history, these changes were local or regional. Forests could regrow, rivers could recover. Earth's great processes, the cycling of water and carbon, the regulation of climate by oceans and forests, the evolution and migration of species, continued largely unaffected by human activity. We were still a small presence on a large planet. That changed with the Industrial Revolution, beginning in the late 18th century. The invention of machines powered by fossil fuels, coal, then oil, and natural gas, allowed humans to multiply our strength and productivity by orders of magnitude. Factories produced goods at scales impossible with hand labor. Steam engines powered ships and trains, connecting distant regions. Cities grew to populations of millions. Medicine advanced, reducing infant mortality and extending lifespans. The human population, which had taken all of history to reach 1 billion people around 1800, doubled to 2 billion by 1927, then doubled again to 4 billion by 1974. Today, there are approximately 8 billion humans living on Earth. 8 billion individual lives, each one a universe of experience, thought, emotion, and connection. We occupy every habitable region of the planet, and some regions that seem uninhabitable. People live in Antarctica, at research stations, on oil platforms in the ocean, in space aboard the International Space Station. We have explored the deepest trenches of the ocean and walked on the moon. We have sent our machines to every planet in the solar system and beyond, carrying messages to any intelligence that might find them. Our species now consumes or redirects approximately 25% of the planet's total primary productivity, all the energy captured by plants through photosynthesis. We use about half of Earth's accessible fresh water. We have converted roughly 75% of ice-free land surface to some form of human use, whether farmland, pasture, cities, roads, or managed forests. We catch so many fish from the oceans that many populations have collapsed. We extract resources, minerals, fossil fuels, timber, at rates far exceeding their natural replenishment. Our agriculture feeds 8 billion people, but depends on massive inputs of fertilizer, pesticides, and water. Our cities are marvels of engineering, but create islands of heat and light that alter local climates and confuse migrating animals. Our transportation networks allow us to travel anywhere on Earth within a day or two, but they fragment habitats and spread invasive species. Our industries produce an astonishing array of goods, but also generate pollution that contaminates air, water, and soil. The burning of fossil fuels, coal, oil, and natural gas has increased the concentration of carbon dioxide in the atmosphere from about 280 parts per million before the Industrial Revolution to over 420 parts per million today, a level not seen in millions of years. This additional CO2 traps heat, warming the planet. Average global temperatures have increased by approximately 1.1 degrees Celsius since the late 19th century, and they continue to rise. This warming melts ice caps, raises sea levels, intensifies storms, shifts rainfall patterns, and stresses ecosystems adapted to historical climate conditions. We are, in effect, conducting a grand experiment on the only planet we can live on, changing its atmosphere, its climate, its chemistry in ways unprecedented in human history and rare in Earth's long story. We have become a geological force, our activities leaving signatures in rock and ice that will be detectable millions of years from now. Some scientists call our current era the Anthropocene, the age of humans, recognizing that we have become one of the dominant influences shaping Earth's systems. Yet this same species that has such enormous impact is also capable of remarkable things. We have built the great libraries that preserve knowledge across generations. We have composed symphonies, written poetry, created art that captures beauty and meaning. We have developed medicine that cures diseases and relieves suffering. We have built telescopes to study the cosmos and microscopes to explore the molecular machinery of life. We have decoded our own genome, understanding the genetic instructions that make us human. Most remarkably, we have become conscious of our place in the universe. We know Earth is a planet, one of 8 orbiting an ordinary star in a galaxy of hundreds of billions of stars. We understand that we evolved, that we share ancestry with every living thing on Earth, that the atoms in our bodies were forged in ancient stars. We can look back across billions of years and trace the story of the cosmos from the Big Bang to this present moment. In 1968, astronauts aboard Apollo 8 became the first humans to orbit the moon. As they emerged from behind the lunar far side, they saw something no human had ever seen before: Earth rising above the moon's horizon. Astronaut William Anders photographed the moment, our blue planet, swirled with white clouds, hanging in the black void of space above the gray, lifeless moon. This photograph, called Earthrise, became one of the most influential images ever taken. Seeing Earth from space changed how we think about our home. From that distance, national borders disappear. Conflicts and divisions seem insignificant. What appears instead is a single, fragile sphere, the only world in all the observable universe known to harbor life. The photograph revealed Earth's vulnerability and isolation, floating alone in an incomprehensibly vast darkness. It helped spark the environmental movement. As people recognized that we share one planet, one atmosphere, one interconnected system of life. Astronauts who have seen Earth from space often describe a profound shift in perspective called the overview effect. They report feeling a deep connection to the planet, a sense of unity with all life, and a recognition of how petty human conflicts appear when viewed from that vantage point. The atmosphere, which seems boundless when we stand on the surface, appears from space as the thinnest blue line, a fragile shell that is all that separates us from the void. We are the only species that can see Earth this way, that can understand what we are looking at, that can comprehend the journey that brought us here. We are made of star stuff, as astronomer Carl Sagan famously said. The carbon in our muscles, the calcium in our bones, the iron in our blood, all were forged in the nuclear furnaces of stars that died before the sun was born. We are, quite literally, the universe becoming aware of itself. This awareness brings responsibility. We understand that Earth's resources are finite. We know that our actions have consequences, that what we do today will affect future generations. We can measure the changes we are causing and predict their outcomes. We have the capacity to choose a different path, to live more sustainably, to preserve rather than consume, to restore rather than destroy. We are not separate from nature, but part of it. We depend on healthy ecosystems, clean water, stable climate. What we do to the earth, we do to ourselves. Many indigenous philosophies emphasize living in balance with the land, taking only what is needed, caring for the environment as one would care for family. These perspectives offer wisdom born from thousands of years of living closely with the natural world. Human cultures are as diverse as Earth's ecosystems. We speak approximately 7,000 languages, each one a unique way of thinking about and describing the world. We practice thousands of religions and spiritual traditions, each offering its own understanding of meaning and purpose. We create music in countless styles, art in infinite variations, literature that explores every aspect of human experience. This cultural diversity is as valuable as biological diversity, representing different solutions to the challenge of being human, different ways of finding meaning and connection. Yet despite our differences, all humans share fundamental similarities. We all need food, water, shelter, and safety. We all form social bonds, care for our children, seek belonging and purpose. We all feel joy and sorrow, love and loss. We all look up at the same sky, walk on the same earth, breathe the same air. We are one species, one family, sharing one small planet. As you lie here tonight, you are connected to all 8 billion humans alive at this moment. Someone is waking as you fall asleep. Someone is being born as someone else takes their last breath. In cities around the world, lights are coming on or going off. Farmers are planting or harvesting. Students are learning. Artists are creating. Scientists are discovering. People are laughing, crying, working, resting, dreaming. You are also connected to all the humans who came before, the countless generations who lived and died, who built and created, who loved and struggled, who passed down the knowledge and culture that shaped the world you inherited. And you are connected to those who will come after, whose lives will be shaped by the decisions we make today, the world we leave behind. Your body carries the genetic heritage of that long human journey. Genes from African ancestors who survived droughts and predators, genes from those who crossed continents and oceans, genes from farmers and herders, from people who endured ice ages and plagues, who adapted to new environments and new challenges. You are the product of an unbroken chain of survival stretching back 300,000 years, and before that, back through the entire history of life on Earth. The atoms in your body tell an even longer story. The hydrogen atoms in your water were formed in the Big Bang nearly 14 billion years ago. The carbon atoms that form the backbone of every molecule in your cells were created in the cores of ancient stars. The calcium in your bones, the iron in your blood, all were scattered across space when massive stars exploded as supernovae, seeding the galaxy with the heavy elements necessary for planets and life. You are, quite literally, made of Earth. The water you drink has cycled through oceans, clouds, rivers, and the bodies of countless organisms for billions of years. The air you breathe has been breathed by dinosaurs, by ancient ferns, by bacteria in primordial seas. The elements of your body have been part of mountains and oceans, of trees and animals, endlessly recycled through Earth's great systems. Humans are Earth's way of knowing itself. Through our eyes, the universe observes its own magnificence. Through our minds, matter becomes conscious and contemplates its own existence. Through our curiosity, Earth explores its own history, learning the story of its formation, its transformation, its long journey through time. We are both ordinary and extraordinary. Ordinary in that we are one species among millions, subject to the same laws of physics and biology as every other living thing. Extraordinary in our capacity for awareness, for wonder, for understanding. We can damage Earth profoundly, but we can also protect and restore it. We can choose, consciously and deliberately, what kind of ancestors we want to be. The Earth does not need humans to continue its great processes. Continents will drift, mountains will rise, oceans will circulate, life will evolve, all with or without us. But we need Earth. We have no other home, no backup planet, no place to go if we render this one uninhabitable. As astronomer Carl Sagan said in reflecting on that famous photograph of Earth taken from beyond Neptune, a pale blue dot in a sunbeam, this is the only world we've got. As sleep draws near, let yourself feel the profound gift of existence. You are alive, conscious, aware, on a living planet, in a vast universe, mostly empty and cold. You can think, feel, love, wonder. You can appreciate beauty, seek truth, create meaning. You are a temporary arrangement of atoms that has somehow become able to know it is temporary, to marvel at its own improbability, to love the world that made it possible. Rest now, knowing you are home, not just in your bed, in your house, in your town, but home on Earth, the only home humanity has ever known. A world that has existed for billions of years before you and will continue long after you are gone, but which, for this brief moment, includes you. You are part of Earth's story, woven into its fabric, made from its substance, held by its gravity, sustained by its systems. You are Earth, looking at itself. You are the universe, aware of its own existence. You are human, a recent arrival, but a remarkable one, capable of understanding the extraordinary journey that brought you here and the precious, fragile, beautiful world that makes your existence possible. Sleep well. Sleep well on your home planet, under its protective atmosphere, held by its gentle gravity, surrounded by millions of species, all sharing this one world. Sleep well, knowing that you are part of something ancient and vast and beautiful beyond words. Tomorrow, the Earth will still be here, spinning through space, and you will wake again to see its sun rise over familiar horizons, breathing its air, drinking its water, living your small but precious life on the only planet we have ever called home. Good night.